pessoas que nos acompanham pelo Instagram. É com grande satisfação que damos as boas-vindas a todos para mais uma edição do Café com Ciência. Iniciativa, como vocês bem sabem, do IF, que une conhecimento de fronteira, ciência de qualidade, café grátis e, sobretudo, diálogo aberto, conversa, discussão com o palestrante. Bom, hoje é um Café com Ciência especial, porque temos o prazer e a honra de receber um pesquisador de projeção internacional, o professor Clemens Burda, da Case Western Reserve University, nos Estados Unidos. Professor Burda é titular da Cátedra de Química e diretor do Centro de Dinâmica da Case Western Reserve University, se as informações procedem, que encontrei. Mas acredito que sim. Bom, pessoal, gostaria de dizer o seguinte, que a trajetória do professor Burda começa na Suíça, na Universidade de Basel, onde ele se forma e obtém sucessivamente o doutorado em fotoquímica. Sucessivamente, no Georgia Institute of Technology, ele se aperfeiçoou em espectroscopia de femtossegundo e ingressou depois como professor na Case Western Reserve. Hoje ele lidera uma das mais produtivas linhas de pesquisas em nanomateriais para a saúde. Em 2023, o professor Burda foi eleito Fellow da AAAS, Associação Americana para o Avanço da Ciência. Essa é a mais antiga e prestigiosa sociedade científica multidisciplinar do mundo. Essa fellowship é uma honraria que, de fato, reconhece contribuições verdadeiramente transformadoras e multidisciplinares. Bom, pessoal, o professor aqui é um químico. Então, por que um químico no estudo de física? Bom, eu diria o seguinte, o professor Burda, de fato, personifica o estado da arte, da ciência do nosso século, onde não há mais barreira entre as diferentes áreas do conhecimento. Então, de fato, temos agora um pesquisador com habilidades multidisciplinares. Depois vamos perguntar para ele sobre isso, se quiserem, vamos tentar entender um pouco mais. Bom, eu só gostaria de concluir dizendo o seguinte. O grupo do professor Burda é pioneiro no desenvolvimento das primeiras nanopartículas direcionadas para tumores de difícil acesso. Ele é autor de mais de 200 publicações, tem uma quantidade grande de orientados, de mestrado e doutorado, vários deles são pesquisadores e professores. E hoje em dia ele trabalha em 3 grandes linhas, que são as grandes perguntas do tempo atual, ou seja, energia, ambiente e saúde. Bom, basicamente é sobre isso que ele vai falar. A palestra se intitula Lighting the Path to a Cancer-Free Future, ou seja, iluminando o caminho para um futuro sem câncer. Então ele vai falar sobre os mais recentes avanços da terapia fotodinâmica, mostrando como a nanomedicina está transformando o tratamento oncológico. Certo? Bom, pessoal, então é com grande entusiasmo então que passo a palavra ao professor Burda.
trying to get on video roll. Because we need. I'm sure we will get there. I was a little worried to give this presentation in English, but then I heard from all the professors that the young people's English is much better than ours. So, yeah. Good afternoon, everybody. Thank you for coming. It's a really great honor to come from far and speak in front of you. It's a very, very educated audience, actually. So I'm almost nervous. And it's my pleasure to talk a little bit about research at the interface of materials, nanomaterials, the photophysics, the nanophysics, and of course how we apply it to medical research, right? So I hope it's going to be a little bit interesting for you, and I try to keep it within 30 minutes so that we get done. Very quickly, I'm up there from Ohio. There is the city of Cleveland. In Cleveland, there is a smaller private university, Case Western Reserve University. It's very research heavy. You see, maybe we have actually less undergraduate students than graduate students, and we like to do research. So within my group, we focus on nanomaterials. My PhD background was on photoscience, photophysics, photochemistry. But then as a postdoc, I switched into a group. They were focusing on nanomaterials. And I still think this is a very interesting avenue to pursue. You see, the nanoparticle playbook is made up of organic molecules as well as inorganic structures. Of many different possibilities. In my group, we work on a lot of them. Most recently, we started making lipid nanoparticle compositions. That is something I will not be talking about. It's interesting. Today, keep referring back to work that we spent over years actually on gold nanoparticles, and they are interesting. Gold nanoparticles are obviously not new. They have been around for well over 20, actually 30 years, but they are just every time providing new aspects, new physics in a way. I show maybe one or two more examples in this talk in the next couple of minutes. So of course, I like to use light as a agent, therapeutic agent, and as a chemical reagent, as an energy input. It's non-toxic, and it comes in many different colors and shades, as you know. Of course, light turns electromagnetic waves, can turn long, become microwaves, radio waves, etc. Or shorter wavelengths where you then have X-rays on the other extreme. I like to use actually the wavelengths that are away from the visible for the very reason that a lot of photomedicine has been done in the visible range. And the problem, the limitation of visible light is, for medicine, it gets absorbed by the skin and barely penetrates any tissue, right? So that is something I thought long about, and eventually, of course, a lot of people go to longer wavelengths because longer wavelengths scatter less and therefore penetrate deeper into the tissue, but not much deeper actually. Maybe another millimeter, another half a centimeter, maybe. So actually, at the end of the talk, I will show you that we move to much shorter wavelengths, and of course, X-rays penetrate the whole body effortlessly, and you can get everywhere. So this is another approach. So the thing we try to do is make our nanoparticle concoction. We inject it into the mouse, into the bloodstream, or directly into the tumor, depending on how we want to address it. Then we give it some time to circulate. The particles, if they are targeted, even if they are not targeted, they start to accumulate in the tumorous tissue, because tumors are just like little sponges, right? So the angiogenesis, it produces a very spongy and open tissue network and arterial network. So the particles, they flow into the cancer and then they don't get out. They actually get stuck there for several hours. And now we can go, and if our nanoparticle concoction is fluorescent, we can actually light them up, shine light on it, take a fluorescence image, and then we can do fluorescence image guided therapy. Right? We can actually know where the tumor is, and then shine light only to the tumor, so that everything else is not going to be affected. That's of course even better if our nanoparticle is non-toxic in the dark and only becomes affected and toxic, it should be toxic, when we shine light on it. Then of course we can have different scenarios. We can either use the photoexcitation to produce excited triplet state, and with the surrounding oxygen, we can produce singlet oxygen and photodynamic therapy. Or we use our excitation and release it as heat, and that uses then photothermal therapy to maybe support another therapy like chemo or PDT, right? So there are two things that are happening: photodynamic, PDT, and secondly, photothermal therapy. Okay, and that is supposed to kill then the cancer cells and cure the cancer if we are lucky. Gold nanoparticles are actually really easy to make. All you need to buy is one precursor and one reductant that will reduce. This is a gold salt, gold 3. You can reduce it to gold 0. You start growing gold nanoparticles. And now you need a solvent system that will arrest the nanoparticle before it becomes too big. Then you do a ligand exchange. Polyethylene glycol is very common. It is very soluble in water, and it is stealth to the immune system, meaning you don't have a huge reaction and proteins agglomerating on them. So now you have this, and then we can actually evaporate the solvent we have used before. Actually, we can also attach dye molecules. They can be fluorescent. They can produce triplet state for ROS production, reactive oxygen species. Then we make sure that we get everything into water, and now we have the dispersed solution. Nano gold is beautifully red to purple, and you will easily find it. So nano gold can be made in all kinds of sizes and shapes. It can be very well controlled. Then you have this initial agglomeration of gold nanoparticles, and once they are dispersed with a good solvent ligand, then they start to, go apart and swim individually in solution. And again, so here we have that solution. They have a core diameter of 5 nanometer and a hydrodynamic diameter of 32. We measure this with dynamic light scattering, and the core diameter, of course, with electron microscopy, right? So now we load these particles with a fluorescent drug, phthalocyanin 4, PC4, and we put them into a cell culture, and what we find is once the drug is being released from the gold nanoparticle, it starts fluorescing, and we can now fit the kinetics of the drug release. It has about an hour time constant, and one thing is interesting, when the dye is on the gold nanoparticle, it doesn't fluoresce at all, because the gold nanoparticle is an energy absorber, so you can excite the fluorescent dye, but it will not emit. It is actually quenched, so it's dark and inactive, and only when it gets into the cancer cell being released, the fluorescence starts. So then we thought, okay, is this the uptake dynamics limited by the cell wall, by the cell, who knows? So we did a much simpler experiment. We take the same particles and put them in an aqueous solution and have another interface to a lipophilic solution, toluene, benzene, and we stir it gently, and then we get the release of the drug into the lipophilic layer, and it has about the same dynamics, actually, time constant, about an hour, and what it tells us is that the release dynamics is actually not limited by the cell wall, it's actually limited by the nanoparticle itself, releasing it. And so that's a great opportunity. That means that one could work on the nanoparticle and actually optimize the release time, being slower for treatments that should go a little longer, or being also faster. So that is something we have been working on over the years. And then, of course, we can study within the cell where these particles are going. They are being endocytosed into the cell wall, then they go into early endosomes, they being released lysosomically, and then end up in the mitochondria. So this is the drug within the cell, this is the mitochondria image, and the yellow sections, they indicate overlap between the drug and the mitochondria. The mitochondria are very rich in lipid membranes that fold, and so it's a perfect space for the PC4 to go in, and they layer actually into the lipid bilayers. So we can see that, and this is just additional support where we image the drug, the nucleus, the cell wall, and so we see that the drug is going into the mitochondria. So we have done a lot of confocal microscopy. Okay, encouraged by the previous experiments, we thought it's time to explore in vivo experiments. So we inject our drug into the tail vein of a mouse. The drug nanoparticles with the fluorophore are circulating in the mouse, and before you know it, well within 1 minute, the drug is fluorescing. Everything that fluoresces here is the drug, because the mouse is non-fluorescent at that point, and so the drug is in the tumor, and we can start therapy. So this is the drug. kinetics in the tumor, the fluorescence of the drug. And so within 1 hour, one can get started, and you have about a day, and then it gets washed out, essentially. And we know pretty well the biodistribution. So these are all the organs that we took out from mice after 4 hours, after we give the drug, 24 hours in red, and then in green after 7 days. And what we see is, so initially the drug is in really high concentrations in the tumor and in the lung, in the blood, of course, that's where it circulates. But then over time, you see the increases here. They go into the spleen and into the liver, and then it makes sense. They filter the bloodstream out and the digestion, and actually the particles, we find them for several days in spleen and liver. The kidney, much shorter lived, it just simply goes through the kidneys into the bladder, and we find it in the urine very quickly, actually. So the particles can be also adjusted. If they are smaller than 5 nanometers, they go through the kidneys and get peed out. And so this is histology. Everything that's black are nanoparticles. You can see for spleen and liver, it gets more over 4, 24, and 7 days here. It's more. But then on the other hand, kidney, these are the filtration cells. First they are full, then they are emptier, and then it's very clean, actually, after 1 day. So that's the dynamics of these particles. It depends on size, shape, surface coating, you know. And so this design we have carried forward into many different directions. One way is to attach a targeting molecule, a small peptide of 12 amino acids that will target specifically to certain tumors. So this is one that targets generally to tumors because it's epidermal growth factor peptide. All tumors like to express growth signals and receptors on the surface because they signal to the environment, I want to grow, I need more nutrients, I need more angiogenesis, and so on. I need more space. And so this is easy to target. And then we see with electron microscopy the particles in the cell, but also how the particles knock on the door and eventually get enveloped into the cell wall. Oops. So this is a cross-section through a tumor where we have non-targeted nanoparticles, and these are targeted nanoparticles. So the difference is here the particles are completely stochastically distributed over the red tumor cells, which have the EGF receptor, and the white are immunocells, which actually don't have the receptor, but the particles are everywhere. When they are targeted, on the other hand, you see all the white cells are completely empty. There's nothing, absolutely nothing. And the red cells are loaded, and some of them are really overloaded, really overcrowded. So this is the difference between targeting tumors and being passively targeted, non-targeted. And one can see that also in terms of fluorescence imaging in the organs. So here's a brain tumor. And so there's a tumor on the right side. If we open the tumor, we see that for the targeted nanoparticle, the fluorophore, the drug is actually going right into the center. So we call this the deep targeting, and that's because of the structure and the physical interactions, really. While non-targeted gets there, because you see there's some fluorescence, but it's much less. It's like factor 8 to 10 on a good day. Sometimes we only see 2 to 4. So it does vary, of course. That's a good example. Just wanted to show, we find also ways to bind the drug covalently, and then we can use light to split the bond, and we studied this very carefully. So, to summarize the first part of the talk, and then there's a second half. So we learned that we can make particles that are biocompatible. We can deliver them to tumors. We can target the tumor with overexpressed cell surface markers, and then have little peptides targeting them. And I show in the second half that we can also target overexpressed enzymes, because cancers produce certain types of enzymes that are part of the cancer machinery, and we targeted these next. And then also we can release the drug either actively, for example with a light pulse, or actually actively by the drug where by the cell, where the cell is producing the enzyme, and the enzyme is now using the protease to release the drug, to splice the bond and release the drug. So we have done that too, and I'm going to show that. And of course, if the particles are smaller than 5 nanometer, they will be excreted very efficiently, actually. So having them small is good. Anything that's bigger than 10 nanometers will be for a long time in the body. So actually, this is one of our new concepts. Cancers, when they are in the body, they start forming tracked, actually, macrophages, immunocells. They're called tumor-associated macrophages. They produce a whole bunch, a list of enzymes. They're called cathepsins. These cathepsins, they are incredibly important for the fate of the tumor. Depending on which cathepsin is actually built, these are enzymes, they can make the tumor grow, they can make the tumor shrink, or they can make the tumor sort of being chewed up, and then individual cells can intravasate into the bloodstream. And what happens next is they get transported away to the next node where they get stuck, and then they stay there, they enter the tissue again, and they extravasate into the tissue and form, of course, a new tumor. That's metastasis, right? We don't want that. So we thought this is good to maybe target metastasis in particular. Let's go and target these, any one of these mechanisms. I like to target these enzymes. There's a lot of inhibitors known. And so we bought some of them and we attached them to our nanoparticle so that we have now on one end a targeting unit that will, in this case actually, we target now prostate cancer, so switching cancer. So we have a targeting unit for prostate cancer, and we attach the drug on the other hand, the photosensitizer, with a cleavable linker that will be cleaved by the cathepsin enzyme. That's but heavily overproduced in the tumor, right? So once we go in the tumor, the drug will be released. And how do we get to the tumor? We add targeting peptides. Okay, so then we see actually here, in pink we have the lysosomes, green mitochondria, blue this is the nucleus of the cell, this is one cell here. We can now see that the bound drug is being brought into the cell. How do we know? Because if we take TEM, we see the nanoparticles in black, and they are already here, and they are here, and they're getting even more over time. But what happens in the meantime is the cathepsin enzyme comes and cleaves the drug off. The drug is being released, and when it is released, it starts to become fluorescent. So the red, which is different from the pink, is actually the released drug, and that happens over time. It takes about 20 hours actually if you do this enzymatically. Now we have the drug released, and we studied, of course, the success of the therapy. So we inject the drug that is cathepsin activity based released. There we have our tumor. We inject it, and in this case we add another thing. That the problem with photodynamic therapy is if you do it in a very short time frame, you bring in all the photons, you start photo damaging the tissue and the drug. There's a lot of photo oxidation happening. So if you actually chop it up into smaller doses, Here we took 3. We tried up to 7, but 3 is the best we found. What you do is you use less dose. You have less effect each time, but they start to accumulate, and they actually get better and better and better every time. And now in the meantime, the blood has time to rinse the site, clean the toxins, and bring in new oxygen. So this pulsed therapy is actually definitely more effective than doing all at once continuously. It's like lasers. Pulsed lasers are more powerful than continuous lasers. So we see here what happens if we take a regular drug molecule and we bring it in and we shine light on it 3 times. It only gets photo damaged. It gets weaker and weaker and weaker. When we do this with nanoparticles, it's the opposite. Every time we irradiate and we let it flush, irradiate, let it flush, do this 3 times. Every time we get higher load of the drug. And that is because after every PDT event, the cell tissue is a little bit more damaged and porous. Next time, more particles go in, more damage. They give it a daytime, and the next time you do it, even more particles go in. So it's actually increasingly successful. And then after several times, so here is the efficiency of red is the cell that we target, blue is the control. The difference is the best on day 3, and on day 7, it starts going down. So 3 is maybe good. So then, how is the tumor growing actually? This is the tumor volume we can measure, and we have this measured for 25 days. If you don't do anything, the tumor just keeps growing, just keeps linearly growing here. You do 1 therapy, it grows a little less. You do 2 therapies, it grows even less. 3rd time, you definitely hit it and start stalling the tumor, right? And so it matters actually hugely. But I can tell you in the clinic, nowadays they do exactly these things. No therapy is single therapy or one-time therapy. Every therapy has repeats and is a combination of things. So this is completely well understood, really. Then I want to tell, we like to go to very short wavelengths. The chemists I need to explain. X-rays is light too, it's photons, right? And it's really good. Why is it good in this case? We know X-rays are dangerous, but 80% of all cancer patients already get radiotherapy treatment. Almost all. That's where everybody ends up. The problem is with the radiotherapy, doctors used to use too high of a dose, 80 gray several times. I know cases, it's just too many side effects. Then the tissue starts falling apart, you can lose organ activity and so on. So what we like to do is use gold nanoparticles as X-ray absorber and enhancer, because gold is much denser and absorbs X-rays 100 times stronger than soft tissue. So it's absolutely beautiful. If we can target the gold into the tumor site, use a dose that can be now 10 times lower. Instead of 80 gray, we use under 10 gray, and irradiate, then we can achieve the same thing with an ultra-low dose of cancer radiation. So here we have the fluorescence image of the tumors. This is a tumor that flu means it doesn't have the receptor on the surface. PIMP has the receptor. Now you see the particles, they all go into the receptor-loaded tumor because there is the interaction, and they don't go very much into the non-targeted tumor. And we also see here with CT imaging the gold nanoparticle density. This is X-ray absorbance through gold nanoparticles here. The fluorescence is higher in the targeted tumor compared to the non-targeted. The number of gold nanoparticles also. And then the tumor growth, if it's not treated, and in fact, the tumor that is non-targeted, this is the flu, not is it? No. It's the non-targeted tumors. it keeps growing, while when we use X-ray radiation, it completely starts to shrink. I'll show you some really good data, but here is sort of our favorite system. Now that's a lot of chemistry, so that took us a year to get there, but we made actually here an organic system that has a targeting ending. It has an end that will, or a part that will bind to gold nanoclusters. These we make really small now, 1 nanometer, 1.2 nanometer in diameter, gold 25 clusters. Then we have here a part that is cleavable by cathepsines. And then we added on the other end a chemotherapy drug. That drug is not good if you inject it into the person. It kills more people than it cures. It's well-known statistics. But if you target it actually precisely to the tumor, now you can lower the dose by factor 10 and bring it to the tumor targetedly. And what it does is when it gets into any cell, it will interfere exactly at the mitosis step and freeze the cell right when it wants to divide, and it will not divide. So the tumor cannot grow after that. So that's one part. And at the same time, we use a very low dose of X-ray that is scattered and absorbed by the gold particles. And so it very effectively takes the tumor out, actually. So this is just characterization, EM, dynamic light scattering, absorption, emission, cell culture studies to prove we can kill the tumor. And the killing is less effective if we add more, it's more effective if we add more cathepsin, which we can add. And that means it's the cleavage, the enzymatic cleavage that releases the drug. And so the mechanism works, and this is what I wanted to show. We can feed these mice. We can, study the targeting. If we target the drug, it's mostly in the tumor. Okay. If we don't target it, it's mostly in the liver. That's just physics, actually. It's just fluid dynamics. That's where it ends up. And then we find actually the particles mostly in the bladder. You can get really strong emission in the mouse. After the experiment, it wants to go pee. And a couple minutes later, it's all in the cage, right? And once the bladder is empty, it doesn't fluoresce anymore. It's all in the bulk of the solution. So this is an experiment that shows when we irradiate this is no radiation, and this is with radiation. If we use here, you see the tumor itself will grow. If we use our targeted particle, no particle, just targeting the chemotherapy, that gives us a very promising result, I have to say, right? But if you use the gold nanoparticles, it will be the green signal here. It goes in and it stays better in, and it actually works even without radiation. If you now use a low dose of radiation, I think this is 8 gray, then you see here tumor growth. Radiation itself is already very helpful, actually. Now, if you have the green one is so our target. If we target our nanoparticle with chemotherapy and some radiation, you see actually we get the tumor size down to 0%. We absolutely eliminated tumors one after another. So that has been so successful that I said here 90%. This is highly conservative, actually. We show, tumor elimination. So we wrote another grant for clinical studies. They go to larger animals first. That's what they're doing right now. And then hopefully it will be going into people as well. So to wrap this up, to keep this within the time limits, so nanoparticles can be very well targeted, actually. Some of them actually bind too good, so we need to adjust the targeting equilibrium. Some of them are just sticking in the tumor. And they can be released enzymatically or with a light trigger or pH induced. And targeting, of course, is in so many ways important because it increases selectivity, but it also reduces toxicity and side effects, right? And I like the extreme wavelength, either longer or much shorter, right? I think it is good to increase the safety protocol of these existing, just a little advertisement. There's a book that you can look up if you like spectroscopy. That's a good book. I like it. I liked it for a long time. There's a journal that's called Spectroscopy. It's an MDPI journal. Whatever your opinion is of MDPI. I'm also mixed about them, to be frank. But I wanted to have a journal that's called Spectroscopy. And we have been doing really well. It's very new, so it is just in the process of being indexed, because so far it was not in any database, but it will be. We have a lot of submissions and it's doing really well. And that's my group. The people who do the work are mostly Zoe, and Zoe is a local kid, a local student. Mai is from Egypt, and every student is from a different country. Hamza from Morocco, Siraj from Bangladesh, Hemal from Sri Lanka, Ju is from China, India, Egypt, Philippines. So yeah, so that's the group. Of course, I want to thank the students who mostly did the work is Sarah and Zoe, and my collaborators on the clinical side. I couldn't do most of it if I wouldn't have them. I used to have my own mouse handling protocol. It's too much work. I went back to do my nanoparticles. It's just too much work altogether. So now I happily collaborate with a BME, biomedical engineering professor, Jim Basilian, and it's fantastic. We got together lots of funding over the years, really, actually. And some other projects are on the Department of Energy side. These are also already for a long time in the works. And with that, I'd like to thank you for the kind invitation. It's really nice and generous of you to make time. And I'm very happy to be here and happy to answer any questions.
Thanks a lot, Professor Burda, for the excellent talk. And we cherish debate, conversation, more than debate. Discussion, let's say this way. So, I open for questions. Pessoal, estamos abertos para questões, perguntas. Se quiserem fazer a pergunta diretamente em inglês, tudo bem. Se não, a gente faz uma tradução. Tentamos fazer uma tradução simultânea. Tem perguntas? Leandro, por favor. Senão o público que está assistindo pelo Instagram não consegue ouvir.
So, Clemens, thank you for the very nice talk. And I think you probably explained, but I think that I missed it. Why they use, I'm not talking about the X-rays, but for the near-infrared, I didn't understand why the use of gold nanopowders, nanoparticles, instead of any other element. The idea behind.
Wonderful question. Why gold? Why gold, right? I mean, it sounds strange and it's expensive. So I can tell you the amount of gold that's used on a nanoparticle is so small that if you calculate how much material you have to buy gold to do the experiment once or treat a mouse, it's like 90 cents. It's less than $1, 5 real, right? So it's so little material that it doesn't matter actually. Number one. Number two is that gold is a non-toxic material, entirely non-toxic. You can inject a lot and it will never affect any animal, any cell. And also, it's very easy to track Because, you know, I like to use carbon nanoparticles because they're maybe even more biocompatible, but actually they're not because they interfere, they're too similar. And when something is similar, it becomes toxic, actually. But carbon, you can never find again in a mouse because everything is carbon. So you look for gold, it's very easy. You can take out a piece of brain, let's say, burn it on a flame, and then look for gold signals in a flame, atomic absorption, spectroscopy. It's completely easy. If you look for carbonaceous, you will only find every time the same. You will never see a difference, you know. So yeah, gold is amazing actually. It's cheap, it's really cheap. The thing that makes chemotherapy expensive is when you have many synthesis steps. If you have to make a molecule and it takes 10, 20 steps to make it, that's so expensive, right? It's human hours, work, labor. Buying a little bit of gold, I mean, actually the bottle costs $500. It's very expensive initially, but once you have it, you can make lots of experiments, and it's very wonderful actually. That's why it's everywhere now in biomedical research.
Perguntas? Bom, enquanto vocês perguntam, I have several questions, but first one, an easy or difficult one, I don't know. The state of art is now studying, researching using mice, right? You just told that next step will be larger, bigger animals. Being realistic, how long will it take to have a clinical study on humans?
Yeah, so okay, to go into, so currently the larger animal study will take 5 years and maybe another 5 years. So within 5 to 10 years we will be going into human studies. Now the human studies will also take, I think, at least 3 times 5 years, another 15 years. And so the average time from a good invention to a good procedure in the clinic is about 30 years. 30 years is how long it takes to escalate, to go from cells to mice to larger animals to humans, 15 years. Evaluation, and then comes the formality. You need to go to the Federal Bureau. They will come back with so many, this is thickness of paper, with 100 pages of questions for you. And then you have another 2 years to respond. So, you know, this is the approval cycle. 30 years is realistic, and so you are young enough. If you start now and get very active in research, you will have a good idea in 2, 3 years, or maybe in 5 years. And then you have the rest of your life to fight for it and defend it. Yeah. But it does take pretty much the lifetime of a researcher, a good part. Of course, in the meantime, you can do 10 other things. It's not the only thing you do, but it will be with you for a while. Yeah, I take the silly questions too. Anything small or big.
Vamos lá, não sejam tímidos.
Thank you for the amazing talk. I think I lost track in the middle. When you're talking in the beginning of the talk, you're talking about visible light, the usual wavelengths that you use before the X-ray part. Which is the usual wavelengths that you use? Because as you mentioned, as you know, it doesn't go deep on the skin.
Okay. Thank you for the wonderful question too. In the beginning, we indeed started using visible light, but we made molecules that absorb long wavelength visible light. So the absorption is around 700 nanometer, and actually 680 nanometer. And the emission that we saw in red is actually 700 nanometer emission, which for some people it counts as near IR. You know, to me it's, yeah, near IR visible, right? And then we decided, you know, should we go even longer? But that's actually a huge problem. And the problem is the physics. Because now, if you make a molecule, you can make a molecule that absorbs at 900 nanometer, and then it emits fluorescence at 950 nanometer. But there are so few detectors and equipment out there that it's really difficult to do even the basic benchtop science, right? And so everything becomes very difficult. And so I started to get, you know, a little bit frustrated with the difficulties to go deeper into the near IR. And so it's, you know, X-ray already exists. Every doctor is using it in the cancer field, and one can build on that. And also, the engineering is getting better and better every year. The instruments are getting more focused, lower dose. It's really amazing how X-ray technology is improving in the meantime, you know. So I think it's easier to improve on the X-ray end compared to the near IR. Yeah.
Not just by the detection scheme, so you need to reach the target. So otherwise, your nanoparticles mean nothing if you cannot reach them.
Mais perguntas? Mais alguém? Por favor.
Good afternoon, Professor. So my question has to do with our current reality. So in your opinion, how will artificial intelligence will transform cancer diagnosis and treatment?
Question, actually. It's in full swing. People are using now AI every day for imaging analysis. So, you know, they used to meet every week once or twice at 6 a.m. Everybody's super tired. Round table discussion, and then they share images, and everybody gives an opinion, and then they make a consensus. Yeah, we think he needs so and so much X-ray treatment. You know, they discuss it now. They use software and AI, and it will look at it, and it will give you an answer. And 99% of the time, it is more accurate than 12 doctors can discuss when they get together. It's unbelievable. So this is an example where AI is the best contribution, actually. Right? Most of the time I think AI is very annoying, right? But there are really, really great image analysis is absolutely fantastic, you know. And it's much fewer over-diagnoses using AI, because AI, if you feed it with the real statistics, it will be much more measured and give you a more objective analysis, because image analysis can be very subjective. And it's loaded with fear, you know, what happens if I don't treat the patient, then it's my fault. And so AI can do this much more objective and more nuanced. Yeah, it's a great, great question. Thank you.
Well, don't be shy. Please, questions? I have a curiosity. You mentioned that it's very easy to produce gold nanoparticles of different shapes. Well, as a theorist, part of my career was on studying electronic properties depending on the shape of nanoparticle. So I'm curious, does the shape have any effect on the efficiency of the process, or is just nano the important?
That is a great question, and not so simple, but I will give you some examples. Yes, it does make a difference, right? as you probably very well know. So for gold, which is a plasmonic particle, right, it makes a big difference if your particle is round, spherical, or if it's elongated. If your particle gets elongated, now you have two plasmonic bands that are a transversal, or a longitudinal and a transversal band, and they oscillate at different frequencies. Now you have two frequencies that you can address. If you use a triangular particle, you get an even broader spectrum and you can address it, you know. In addition, when you get more directions, or like a star, for example, now you have spikes and you can create hot spots, hot plasmon spots. They are very particular and one can utilize them for even more, you know, for different things, for sure. So this is used a lot in catalysis. It can certainly be used in biology. There are probably not as many examples as there should be. It's a little harder to make really good shapes, very reproducible, and then to use them intelligently. Right, there's always, in reality, there's always dispersion, shape dispersion and size dispersion. So, of course, that will always cause some, you know, a little bit additional uncertainty, of course, no matter how great the synthesis is. But overall, of course, it's a very great concept with lots of opportunities. Yeah. So yeah, size and shape hugely matter actually. Yeah. And the easiest is the sphere, and it's great to get started with. Yeah. Right? Spheres is of course the thermodynamically most stable shape because it minimizes the surface area for the same mass. And when one can make cubes, for example, and when you shine laser light on it, they get too hot, they start to melt and form spheres. Or rods or stars, they will always form spheres when they get too much radiation. Yeah. So we can see, so that's actually a good indication that too much radiation was in a place. Yeah, if we would use stars just as a precaution not to use more radiation, that could be a good safety measure. Yeah, that's right.
Just touch on one point. I'm curious. Here, I'm amateurist, but there are many experimentalists who study hyperthermia, thermal effects. What about this gold nanoparticle? When irradiated with a small wavelength, thermal effects are important for the body, for your kind.
Oh yeah, this is it's a big topic actually that I didn't go into because I didn't want to go too long. But if I would quickly give you an answer, gold is so wonderful because it absorbs heat or light very effectively, and then being a relatively heavy atom, it releases heat quite well. It's a good energy sink. And therefore, it also quenches fluorescence. When you attach a molecule like this indocyanine green, it will not fluoresce. The phthalocyanine I showed earlier will not fluoresce, but it can absorb light. And then the gold nanoparticle is absorbing the energy and release it as heat. Now, what happens is, so this is indocyanine green. It's already on the medical market. What we can show is actually when we use indocyanine green, so if we shine light on cells, they get maybe 30 degrees hot. If we use ICG and also gold nanoparticles, actually, it's the same effect. Actually, it's even better. Then we get a huge temperature increase. Gold nanoparticles and ICG are very similar. They absorb light and they release heat very effectively. So now we can reach temperatures of 50 with gold. We can get to 60 degrees. And that's just about right. It doesn't kill the body, but it is hot enough. If you leave it for several minutes, 5 minutes, 60 degrees will definitely kill the cell. That's about the limit. And, you know, one can calculate then the photon density and the photon flux. So this is molecular calculation. But the idea Yeah, it's exactly. So we actually work on this very focused because I believe photothermal is such a great opportunity because it's not a chemical treatment. It's a physical treatment. And the cell can, when you treat it with chemotherapy, it will always find metabolic deviations, to find a new pathway to grow without, even if certain things are killed in the cell, it will find resistance, chemoresistance to the therapy drug. But it can never find a deviation when it gets too hot. This is the end of the cell, right? So I actually think photothermal therapy is really, really important. And we are studying it a lot, actually. This is, so actually we are showing here, this is a tumor before and the tumor after. It shrinks. And also the survival, wow, this is actually, yeah, so the survival rates are fantastic. This is animal survival, 100% all the way to the end. It's incredibly powerful. Without treatment, here the control, after 30 days, every mouse is dead, And then you can do surgery. See, surgery alone and fluorescence image guided surgery, it improves the situation, but only 20% survival. While photothermal therapy, it's amazing. Yeah, it's clinical. These are studies right on large numbers of mice. It's crazy. Yeah, this is actually currently under review. It's coming out. Yeah. I'm very glad you asked. The thermal effect is so important, and again, that's why, whenever you think you're tired of nanogold, then suddenly you have a new application. This photothermal is really great, and nanogold is wonderful, but also molecules can do that. Certain molecules are good at this. Yeah. Definitely, in my opinion, one way forward. You see, in cancer, it's like in energy research. There is not one way or one best way. You have to have a multitude of many modalities, and then the experts in the clinic, they find the right mixtures, or AI in the future, and this is the way to go. It's always going to be a mixture.
Ok, bom pessoal, mais alguma pergunta?
Hello, Professor. First of all, thank you for joining us today. And I have a question about I read your last article, and you showed there the gold nanoparticles speed up the treatment in days in hours. So, physically speaking, what is the reason about the speed up treatment? Like it's due to the cell observation, or it's because the application of electromagnetic field? And that is my question.
Let me see if I understood your question right. Were you asking what is the reason for the accelerated tumor shrinkage? Yeah. So it's essentially an instant effect. Let me point simply to one slide. Let's see. I think it's back there. So essentially, here. Here, for example. If you, oops, maybe I lost the connection. It's okay. So when you heat your tumor to, 50, 60 degrees, it's instant death. Usually it will take days for the tumor to grow, right? Every day by a few %. And it's a slow and painful process. But in this case, you can, have this done in 1 day, maybe in 3 days if we do it step by step. but the results essentially happen, the dying of the cell, the apoptosis, and then the tissue rearrangement, and then of course, you know what happens? It becomes soft, the cell starts to dissolve, and then it will have to actually be flushed out by the metabolism. It takes about 24 hours. So yeah, it's of course hugely accelerated, right? Yeah. And so light is amazing as a reagent. I like working with non-toxic things. I really hate working with toxic molecules, but sometimes you have to do that for a little bit. But I really try to minimize it. Light and gold and heat. It's amazing, right? Yeah. And it's fast. Yeah. Thank you for your question.
Ok, pessoal, mais perguntas? Então, já deu 2h15. Eu gostaria de convidar todo mundo, o professor Burda vai ministrar mais uma palestra mais tarde. Let me announce the next talk. You are exploited today. He will give another talk 4 p.m. Where? Upstairs. Okay. Bom, you are all invited for the next talk. I don't know the title of the talk. Do you know? Good. But it's about nanomaterials. Ok, bom, teremos mais uma palestra então mais tarde às 4 horas. Vamos deixar o professor também descansar um pouquinho. Quem quiser conversar com ele, pode conversar aqui, tá bom? Então vamos encerrar, vamos agradecer de novo. Thanks a lot. E vamos fazer as fotos direito. We have some pictures for the divulgation social network. Quem que vem fazer as fotos?